So the way we're going to do this for gas laws, there are a couple different methods. Like I told you, I'm going to go a little off script and off of this, and we are going to start at the end of gas laws and work our way backward. And I think that's a different way of understanding this, and we are going to try it. So your goal in this class, all of you, is to get a better grade on the quiz next week on Tuesday than the people in second hour. Okay, that's your challenge. So I need you to lock in and put your phone away. Gregor. So, all right, so let's dive into this. So to get into this, this is gas laws. We're going to start with, whoa. Holy God. Helgus, did you get all this? Of course. Thanks so much. Dang it. All right, so what did we do yesterday? We did a lab. Thank you. Yes, what did we do? Yes, so we had a pipette. We filled it with water. What did we do next? Sealed it and then compressed it, right? Stacked books on top of it, okay? What were the two things we were measuring / observing yesterday? The volume and what did the books represent when we were stacking books on top of this? Pressure. All right, so we were looking at the relationship between pressure and volume. I suppose I should write this up here. Nope. What did we find about the relationship between these two things? The more books. Was it though? Think about it. Hold on. I know yours. Think about what happened to the volume of the air. Remember the volume of the air. Decreased, right? So as we went higher here, what happened to the volume? Higher pressure led to lower volume. This is what we would call in the world of math and also the world of science an inverse relationship. Right? As one gets higher, the other one gets lower. So this was yesterday's lab. That was the giant aha that you were to take away from that lab yesterday was, hey, as we kept stacking more and more books on top of the bulb of the pipette, the volume continued to get smaller and smaller. You guys made those observations, right? You put them into a graph, you answered some questions, but this was the big relationship here was pressure and volume. As pressure got higher, volume got lower. So you are not alone in these sorts of observations. Scientists have also done similar experiments where they compared things about a selection of gas. They compared things like pressure and volume, and they had one other one that they compared called temperature. And where we're going to start today is at the end. We're going to start with the combined gas law. How do I want to do this? I want you to write this real big in your notes. This whole mess. That's a T with a little button hook on the bottom, so we should probably just write it. Yes. This is what you need to know about the combined gas law. And this is how we're going to use this thing. The ones and the twos stand for like initial condition and then changed condition. So if you multiply pressure and volume and divide it by temperature of a selection of gas, and then you change one or more of those things, when you remeasure and redo the math, they will be equal on the other side. Okay, so have this real big. This is the combined gas law. If you can remember this, you will be fine for next week's quiz. PV over T equals PV over T. And now there are some caveats to this that I want you to know. So underneath this, I want you to put two, I don't know, asterisks or something. Let's just do that. I don't know how to spell asterisk either. A-S-T-E-R-I-C-K-S? I don't know. All of your units must be the same for each of these things. So where you have pressure on the left in, let's say, kilopascals, you would need pressure on the right in kilopascals. A Newton per square meter, but that's not important right now. It's a measurement of pressure. Okay, cool. Volume, same thing. If you have liters on the left, you need to have liters on the right. You can't have liters and cubic inches. You can't have, I don't know, pick another volume measurement, gallons and cups. The units must be the same. Now, not the same unit for all three of these because you have different dimensional units. You have pressure is pressure, volume is volume, temperature is temperature, and that leads to the second asterisk. Temp must be in Kelvin. Anybody remember this? Kelvin? Yes, you do. Yes, you do.
Are you sure?
As an aside, thinking about the math here, why couldn't we use Celsius or Fahrenheit? Look at this formula and tell me why, just with algebra rules. Why not? You could have a negative in a denominator. If you had negatives in this formula, yeah, how can you have a negative pressure? How could you have a negative volume? What does negative volume mean? Even worse, how could you have a 0 for temperature? What if we just had a sample at 0 temperature? What would that do? What's that? Yeah, we'd have a 0 down here, and that would be also a mess. Right? So yes, we can't have negatives. We really don't want zeros either. Right? So we have to use the Kelvin temperature scale when we get into working with temperature. So this is the combined gas law. Now today, because we're introducing this, yes, sir.
Does a black hole have volume?
That's a great question. That's a question that I'm not going to answer here today. Does it have volume? What part of the black hole are you talking about? Are you talking about from the event horizon in, or are you talking about the singularity? Because the singularity technically doesn't have volume, like the middle of the black hole. There's a spot in the black hole where if I go past this line, right, here I'm outside the black hole, here I'm inside the black hole, and then, you know, it was great knowing you. Well, there's one in the center of our galaxy, in the center of the Milky Way. Yeah. It's true. If you've ever been to Gary, Indiana, that's kind of the black hole of the Midwest. Yes.
And so, like, those things, once they enter the black hole, they're just not no longer. So my sunglasses
It's complicated, but yes. Technically, yes. All right. We were talking about gas laws. Somehow, we devolved into black hole discussions.
What's the negative volume?
3, maybe 4 years. Yes. I'll miss all of you terribly. So a black hole is a gravitational thing, just like the sun is a gravitational thing. Like the sun has gravity, a black hole has gravity. We orbit around our sun. things orbit around the black hole and will orbit around it indefinitely. It's not like a vacuum cleaner that just everything, it's a gravitational spot, and there's a bunch of stuff that just orbits a black hole. So instead of a sun in the morning in the sky, you'd have a black hole instead. Yes, what happened? Ours right now is not currently actively consuming like a star or something. So it's just like a black hole in space. It's like instead of a sun, a black hole. Uh-huh. No, no, we'll be good. We'll be good.
When will it start taking?
It won't. It
Like April and
that's like saying here, hold on. That's like saying how long until we get sucked into our own sun and burnt alive?
How long until the sun explodes?
Well, that's a different thing. But we'll never, we are in a stable orbit around our sun. So we will never, crash into the sun. Same thing with a black hole. If you plucked out our sun and put a black hole in its spot, I mean, it would be bad, but we wouldn't get sucked into it.
no heat.
We would still orbit around just a black hole, which would be bad because there's no heat coming off of it.
Well, I'm not worried about that.
Oh, well, I mean. No. No. We're in a stable orbit.
So there's like and like there's gravity being pushed away like the black hole
Our angular momentum, if the sun suddenly disappeared, there was no sun. We are moving at, I don't know what the number is, 50 kilometers per second. That's really fast. That's here to Chicago in a second, right? Give or take. So the Earth is going really fast, and if all of a sudden there wasn't gravity pulling us in, we would just shoot out at 50 kilometers per second in a straight direction. The sun pulls us in. So it's that balancing act of we're trying to go this way, and the sun's trying to push us in, and we end up just going round and round. Right? So, Helgeson, we're going to have to cut all this stuff out.
Don't cut it out, because that's actually such a.
I know, but that has nothing to do with gas laws. So somebody tuning in for gas laws is going to go into this
You should, like,
black hole
clip
thing. It's
stuff
going to be bad.
out and put it into another video.
Make it its own video.
Ah, so we take that snip, make it a black hole discussion. I don't hate that idea.
just say like skip to 2 minutes and 50 seconds if you don't want to listen to us.
Nobody wants to do that re-click. They'll be irritated and they'll tune off and go watch Henry's Twitch channel. We don't want to lose views to Henry. Bruh.
You said you put your hand up.
No throwing stuff.
I didn't throw anything.
Of course not. All right, so let's get back to gas laws. What we are going to do today, we're going to go back in time into this thing. Now that we know where we're going, we're going to go back in time. We're going to talk about a scientist named Robert Boyle who did some work along this same line, specifically just like we did, where he looked at the relationship between pressure and volume. He did not consider temperature. For Boyle's law, temperature remains constant. So in the initial measurement and the final measurement, we assume the same temperature. So just like you would in algebra, if these are the same number, do they matter? No, we can eliminate them, right? If you take two sides of an equation and divide by the same number, you still have the same number. Okay? So now we're going to go back to Boyle's law. I can do that by hitting this button. No, we're doing just one law today. We started at the end. We're going to actually skip this for a second too. All right, so here's our guy, Robert Boyle. Not only exceptionally handsome, he was a philosopher, a chemist, a physicist, an inventor, and a gentleman, Henry. I don't know, a scientist is a gentleman, a super polite scientist like you, Henry. British. I don't know why British is like the top of the thing here, but fine, he was British, whatever. So he did the same experiment you did yesterday, only he probably didn't use the same materials. He probably did, more sciencey stuff. But he figured out also, just like you did, you don't need all that. Who cares? It was up there. No, I'm not going back. I'm sorry. Physicists, gentlemen, what else do you need? I'm not British. Who cares about all that other stuff? He was British, for crying out loud. He was obviously a gentleman. So Boyle figured out in some sample of gas, the pressure and the volume were related inversely. And he also figured out that if you multiplied those two things together, you ended up with a constant. It's the same number every time. That's what this K stands for. So this was kind of what you were supposed to figure out from your graph on the assignment yesterday. You were close. So this is Boyle's law. PV equals K. Put in a more, succinct manner. You can just watch the video later. Just don't get distracted by the black hole conversation. It's true. It's true. We got to get through all this. We've only got an hour left. So this is the definition of Boyle's law. I will promise to give you enough time to write this whole thing out if you would like. Oh, okay. She's still backed up. There's a traffic jam on your notes. Henry, you got to put that away before I lose patience. You don't want me to lose patience. You got a lot of great questions. I don't know. C is kind of in science. C is the speed of light. K is just generally a constant. C is the speed of light, so you kind of want to stay away from C as a choice for constant. Everybody got this? Okay. Take our time. You got this. I feel like we're getting close. We'll have to cut out this part too. Just this giant dead space waiting on Miranda. Now this is how we're going to use this. You don't necessarily need to write that part at the bottom. But when we're talking about Boyle's law, this is how we're going to use this equation. PV equals PV. On the left, you have the initial condition, and on the right, you have the changed condition. So if you start with some pressure and volume and you change the pressure using math, we are going to be able to figure out what the new volume will be. I know. Just wait. It gets way worse before it gets better. So PV equals PV. Let's use it. Let's try one. This is how to solve these equations. First, you write your formula. PV equals PV. P1 times V1 equals P2 times V2. And then you start listing out what they are. And I'm going to make a statement that the harder part of these is figuring out what's what. The easier part is the actual math. because these are going to be in the form of a word question similar to like you have here, where you need to read through this and know what they're talking about. Atmospheres here is the unit for volume, or for pressure. Volume, stop it. So atmospheres is the pressure number, and liters is what we're using for our volume measurement. So let's do some math. P1 V1 equals P2 V2. And now we start filling in the blanks. So now we have a math problem that we're trying to solve for V2. Again, you guys all should know how to solve this for that variable V2. Because on the left, it's P times V, and on the right, it's P times V. So to solve this, we just divide out by our 0.88. We get, what do we get here? Somebody do the math. And again, we keep our units in the same units. We started with liters as our measurement of volume. We are going to end with liters as our measurement of volume. So this is how we apply Boyle's law. And again, Boyle's law is just a small subset of that combined law. We're going to talk about Charles tomorrow, Gay-Lussac on Friday, maybe? The combined is just 3 different rules combined, and we're going to talk about all 3. That's the baby bird thing I was talking about. What do you mean correct? Yes. The scientists? You mean? No, we got one more thing. Everybody got this figured out. Sample problem. So the other thing we need to talk about is what happens if I told you need to use all the same units. What happens if they're not?
Oh my God, no. A T-chart.
Oh no, a T-chart. Somebody spotted a T-chart. Look out.
No.
Love me some T-charts. So we just talked about standard temperature and pressure. Today we get to define what it specifically is. I know. Weep. So those 4 things under standard pressure are all equivalences you can use in a T-chart. So if I give you millimeters of mercury, and I want you to convert that to atmospheres, you now have a way to do that. If I give you kilopascals and say convert that to atmospheres, again, you can now do that. Those are 4 things that are equal, just like 36 inches and 3 feet and 1 yard are all the same. Torrs are just a unit for millimeters of mercury. I know. Science hates us. I won't get into how pressure was measured here. That's more of a physics thing. Maybe we'll do that next year. And then lastly, the standard temperature for STP is 0 degrees Celsius or 273 degrees Kelvin. But we'll talk more about that later this week when we get into Charles' law. So let's do an example. Huh? In her defense, when she writes something down, Henry, she's able to read it later.
I can read it later.
Yep.
You might be able to read it.
How come you can read it, Henry, and no one else on planet Earth can read it after you're done?
I got my own special code.
Special code. Your writing is encrypted for safety. That's smart. That's really smart. I like where you're headed with that. Okay, so this doesn't look like a T-chart here, but it is a T-chart. If you imagine this as a line like this and like this, all of a sudden this starts looking like a T-chart. If we had to convert to atmospheres, start with our 720 millimeters of mercury and then use our conversion factor inside a T-chart, and this comes right from those equivalences that you just wrote down several seconds ago. The next problem is the same thing, just instead of starting with millimeters of mercury, you start with kilopascals, and it works the exact same way. And again, keep in mind what we started with combined laws. For any of this to work, you have to be in the same units. So if you're in pressure units of kilopascals, you're going to end in pressure units of kilopascals. You need to make sure all of your units are the same for any given dimension in these equations. What does what equal? Oh. Mr. Helgeson, I think we're good here.